All right, so I want to concentrate on doing a couple more types of equations that we haven't had examples of yet. Then talk a little bit about how we do a couple on the calculator, and then talk a little bit about the take-home quiz that you'll have for Friday. So I want to go look at this number 5 here. I think I might have solved this one last time. I don't remember when we did a general solution, but I know that some of the problems in Hawks ask you to find solutions in 0 to 2 pi. So I want to talk a little bit about how we do that in this particular context. So we approach this one for number 5 like we would with other types of problems. The first thing we want to do in this case is we want to try to isolate the sign. So we will add the 1 to the right-hand side, and then divide by 2. So we see that the sign has to be equal to a half. So since the sign is positive, what quadrants are we looking in?
1 and 2.
1 and 2, good. So I need an angle over in quadrant 1 that has a sign that's 1/2. What angle over in quadrant 1 has a sign of 1/2?
30 degrees.
30 degrees, which is the pi over 6, good. And so then we also need the one that's over in quadrant 2, which is
5 pi over 6.
the 5 pi over 6, cool. All right, so to get a sign value that's equal to a half, whatever the angle is on the inside has to be one of those two. So in this case, the inside looks like 3 theta, so we'll write it as 3 theta is equal to pi over 6, or 3 theta is equal to 5 pi over 6. And then much like what we did last time, we use the fact that a sign has a period of 2 pi. So we'll add multiples of 2 pi here, just like we did before. The last thing we need to do for this one, though, is we just need to get theta by itself. So to get theta by itself, we'll divide both sides by 3. So when we divide the pi over 6 by 3, or think about multiplying it by a third, we would have pi over 18. And we also have to divide this one by 3 as well. So we would have 2n pi over 3. Or do the same thing over here. We would have 5 pi over 18 plus 2n pi over 3. So if this was asking for all solutions, this would be all solutions. Remember, n is representing any integer, so we can plug in anything we want in for n that's an integer. So 1, 2, 3, 4, whatever, 0, -1, -2, and so on. This would be your general solution, but some of the problems ask you to find the answers from 0 to 2 pi. All right, so if you're asked to find all the solutions in 0 to 2 pi, we actually have to plug in some numbers for n to figure those out. So the first one we can plug in is n equal to 0. And we get, if I put in 0 here and here, we'll get pi over 18 for this one, right? Because the second piece just goes away. If we put in 0 over here for the second one, we get 5 pi over 18. So there's 2 of them. But there's going to be some more as well. So let's check another one. Let's do n equals 1. So what that means for the first one is that you would have pi over 18 plus 2 pi over 3. So we're plugging in 1 for the n. If I get a common denominator here, if I multiply top and bottom by 6, I would get 12 pi over 18 plus another one. So this one will be 13 pi over 18. I do the same thing for the second solution over here. I would have 5 pi over 18 plus 2 pi over 3. We just said that was 12 pi over 18. Plus a 5 gives me 17 pi over 18 then. A little bit bigger. Not quite so big. All right. So we found 2, and we've got 2 more. We can do this again for n equals 2. When I put in 2 for n, I get 4 pi over 3. Again, getting a common denominator, multiplying top and bottom by 6, I would get 24 pi over 18, plus another one gives me 25 pi over 18. Do the exact same thing for the second one. Oops. 4. Do the exact same thing for the other one, plugging in 2 for n. I get, this is 24 we just said, plus 5 gives me 29 pi over 18. This seems to be pretty tedious, which it is, just plugging in these individual numbers. However, we have to know a place where we stop, right? We're only looking for 0 to 2 pi. Eventually, we have to quit. We can check pretty quickly that all of these are less than 2 pi, because if I do 2 pi and multiply it by 18 over 18, that's a 36 pi over 18, and all of these are less than 36 here. Now, the good news is that we're done. We don't have to find any more, because if I put 3 in for n, I'm going to get 2 pi, right? If I put 3 in for n, I'll get 2 pi. If I take 2 pi and add something to it, I get something that's bigger than 2 pi. So notice I know that I'm done here. Notice we started with this coefficient of 3. I plugged in 0, I plugged in 1, I plugged in 2. When I start at 0 and go to 1 less than this 3, I'm done. That's all the solutions I need. So these two, and these two, and these two give me the 6 solutions here. Another way that I know that I'm going to get 6 solutions, notice originally how many solutions did we get before we divided by 3? How many did we get? We got 2, and then with this 3, we ended up getting 3 times as many. So I knew that I was going to get 6 as well.
Wait, can you say again how you knew how many solutions you were going to get?
Okay, so I knew that I was going to get 6 to start with because before I divided by this 3, I had 2. I had these 2. So as soon as I got those 2, I knew I was going to get 3 times as many because of this 3 out in front. Okay. Remember that when we think about this with the graphics, when we do this graphically, this changes our period. We would divide the period by 3, which means that the graph ends up getting drawn out 3 times as fast. So you're going to get 3 times as many solutions. That's how I knew I was going to get 6 to start with. Other questions on that? Okay, let's see if we can find another one like that. Or I may make one up, see if I can find another one on here pretty quickly. Okay, let's look at 13. Let's do one with tangent here. All right, so this one we would add the root 3 over and then divide by the 3. So we have to figure out, tangent's a little bit nicer than at least in my perspective, the tangent's a little bit nicer than the sine and the cosine ones because tangent just has a period of pi. So for tangent, we find the solutions in 0 to pi rather than 0 to 2 pi, and then add multiples of pi to it rather than multiples of 2 pi. Because remember, the period for tangent is pi rather than 2 pi. So when we do the general solutions for tangent, we only have to worry about from 0 to pi to start with. rather than 0 to 2 pi. The reason we do 0 to 2 pi for sine and cosine is because the period is 2 pi. But for tangent, we only have to worry about 0 to pi. So we only have to worry about quadrants 1 and 2 for our purposes. All right, so we see the tangent's positive, so we're interested in quadrant 1 in this case. We need an angle that gives us root 3 over 3 for the tangent, and I think we can check that pi over 6 will work for that. So I can write the 2x as pi over 6 plus n pi. If you're thinking about doing the one in quadrant 3, you can absolutely do that too. You could write it, the one in quadrant 3 would be 7 pi over 6. But again, this one's going to take care of that because remember the period is just pi. If you plug in 1 for n, you get 7 pi over 6 for this one. And then to get to our general solution, we would divide by 2. So that would be our general solution. So if the solution, or excuse me, if the problem just asked you for all solutions, you would be done at this point. If you are asked to find the solutions from 0 to 2 pi, because that is some of the typical instructions for this one, we would start with n equal to 0 and plug in numbers for n until we get above 2 pi. So if n equals 0, we would get pi over 12. If n equals 1, you get pi over 12 plus pi over 2. That gives you 7 pi over 12. Now, tangent's nice in the fact that I only have to look for solutions from 0 to pi because the period's pi. But the thing I told you about sine where I could stop at 1 less than what we had here doesn't work for tangent. I have to go a couple of more here. So if I do n equals 2, I have pi over 12 plus pi. Gives me 13 pi over 12. And if we have n equals 3, we would have pi over 12 plus 3 pi over 2, which gives me, what, 19 pi over 12. Now I'm done. I have these 4 solutions. Again, this one I can tell that I'm done at this point because if I plug in 4 for n here, I'm going to get 2 pi. And if I take 2 pi plus something, I'm certainly going to be bigger than 2 pi. Now again, the only reason why you would have to do this part at all is if you're asked to find all the solutions in 0 to 2 pi. Again, Hawks has solutions that ask you to do that. So my general take on doing that is to first find the general solution, which is what we did here, and then start plugging in values for n until I get all of my solutions from 0 to 2 pi. Questions on that? Okay. Well, let's talk about some of these where we have to use some identities to help us start the problem. So let's look at number 16, this one that's right below here. All right, so we have 2 sine squared x and then plus a cosine x is equal to 2. So notice since we've got a square and a single power, it's not going to be easy to try to isolate a trig function here. So we're going to want to factor if we can. So that's going to, and when we get these quadratic ones, that's going to be our big technique. If we can't isolate the trig function, then we're going to need to factor before we try to isolate. We did a couple of the factoring ones last time. But in order to be able to factor this one, I need to get everything in terms of the same trig function. Trying to factor something with a sine and something with a cosine in it isn't going to be very useful for us. But I do know something that I can plug in for sine squared that's in terms of cosine squared, or in terms of cosine. So we can plug in 1 minus cosine squared x for sine squared. And get the 2 times 1 minus cosine squared x, and then plus cosine x equals 2. And then we'll solve this just like we were trying to solve anything else that we're trying to factor. So the first thing I'll do is distribute the 2. And then remember, if we're going to solve by factoring, we need to get 0 on one side. So I'm going to subtract the 2 over. When I subtract the 2 over, notice that they cancel in this particular case. So I'm left with 2 cosine squared x plus cosine x equals 0. And now I can factor out the cosine. I can factor out a cosine. And I'm left with minus 2 cosine x plus 1 equals 0. Now that we have it factored, we can set each piece equal to 0. So we have cosine x is equal to 0, or minus 2 cosine x plus 1 equals 0. We rearrange the second equation. We have cosine x equals negative a half. So now we are ready to write down our general solution. So if we want to write down the general solution here, we need to know, first one says we need to know where cosine is equal to 0. Let's think about quadrants again. So cosine is your left or right? It's the adjacent side of the triangle. So if cosine is 0, we have to be on the y-axis, essentially. Our angle has to be there. So your x would be pi over 2, or 3 pi over 2, right? Pi over 2 gives me a cosine of 0. 3 pi over 2 gives me a cosine of 0. And then for each of these, we would put in a multiple of 2n pi. For the second one, the cosine is negative. What quadrants is the cosine negative in? What quadrants are we looking at?
2 and 3.
Yeah, 2 and 3, right? So I need a cosine that's a half but negative. So if I'm over here in quadrant 2, which one is that going to be? Well, what angle would give you a cosine equal to a half if we were over here in quadrant 1? What angle has a cosine of a half? It's a pi over, that would be the 60 degrees, or pi over 3, right? So this one over here must be 2 pi over 3. And we would add a multiple of 2 pi to that. The one that's down in quadrant 3 would be 4 pi over 3. So this would be your general solution. And in this particular problem, if it asked you for the solutions from 0 to 2 pi, you wouldn't even worry about the multiples of 2 pi here. You would just have these particular values. Questions on that one? All right, let's see if we can find another one here. I want to use an identity first. Let's look at 23 here. So notice that we've got a cotangent squared and a cosecant squared. If we're going to try to factor these, we need to be able to get this to a point where we can have the same trig function all the way through so that we know how to factor it. So we remember that it doesn't matter which one we replace. I will replace the cosecant squared in this case. I can replace cosecant squared with 1 plus cotangent squared. This one's not too hard to isolate now because I can move this over to the other side. I get cotangent squared. If I move the 3 over, we would get 4. So we get cotangent squared of theta is equal to 4. So we get cotangent of theta is equal to plus or minus 2 when we take the square root of both sides. And in this one, I think I'm going to convert it over to tangent. And get our tangent is plus or minus a half. Now, this doesn't look like one that we know the tangent value off the top of our head, right? This is not a tangent that we know. So this is going to be one of the problems that we're going to need to use our calculator to help us. So let's talk about that a little bit. We're going to do a few more examples of this with the calculator as well. But let's say this is really representing two equations, right? Tangent of theta equals a half, or tangent of theta is equal to negative a half. Let's concentrate on the first one. So let me pull up a calculator here. No, I should have. Before I do the calculator, to get theta by itself, let me just concentrate on the first one to start with. To get theta by itself, I would have to do inverse tangent of a half. Okay? Because I don't know what the tangent or what theta is off the top of my head, that when I take the tangent of it, I get a half. So I need to use my calculator to get at this one. So let me flip over to a calculator here. All right, so I want to do inverse tangent, and then I want to take 0.5, and this will tell me if I'm in degrees or radians. Okay, I'm in radians here. So when I do inverse tangent of a half, I get this 0.4636 number. So let me go back over to where we were. So that was 0.4636. So this is 0.4636 about. But we have to remember some things about tangent, because one of the things we want to do is to try to get either all solutions. I mean, the two directions that you're going to get are going to be all solutions to the equation, or all solutions between 0 and 2 pi, or between 0 and 360. Those are the only possibilities that you're going to get for directions. This number here is over here in quadrant 1. So this angle being that 0.4636, given to you in radians in this case, with that angle being 0.4636, is it over in quadrant 1, because we need to remember that when we do inverse tangent, it gives you an angle in quadrant 1 or quadrant 4. It's the only places it gives you those angles. Okay? But there's another spot where the tangent's going to be equal to a half. It's going to be over here in quadrant 3, right? Tangent is also positive over in quadrant 3. So there's going to be another angle over here in quadrant 3 that's going to have the same tangent value. Now, the way I know how to find this angle is because this has to be the same reference angle. This still has to be 0.4636. So to get all the way around to there, the other one is going to be pi plus that, because it's 180 degrees from it, right? If I go from here to there, it's 180 degrees. So when I find the one that's over in quadrant 3, I need to add pi to it. And then if you want so these would be your two solutions in 0 to 2 pi. If you want the general solution, you would add multiples of pi to each of these. So if you want the general solution, you would do plus n pi. I'm just concentrating on the finding the ones in 0 to 2 pi right now. So this one's in quadrant 1. This one's in quadrant 3. Everybody okay with that so far? Okay. All right, let's look at the other one. I have to do the same thing here. I have to do the inverse tangent to get me an approximation. So I do inverse tangent of both sides. Well, I can go back over to my calculator, but I can tell you right now that if I use my calculator, this is going to give me negative 0.4636. Because remember, again, tangent, the inverse tangent gives you an angle between negative pi over 2 and pi over 2 in quadrant 1 or quadrant 4. This is certainly a perfectly acceptable answer to the original equation. However, if you're being asked, let me draw a different picture instead of putting that on there. If you're being asked to find all solutions from 0 to 2 pi, then I have an issue because I just got a negative, and that's not between 0 and 2 pi, right? So I have to use some knowledge to get the other angles for tangent. Well, I'm down here in quadrant 4. I know that tangent's also negative over in quadrant 2, right, up here. So I can get to that angle by adding pi to it. This would be your quadrant. This would be your quadrant 2 angle. Now again, this number is not between 0 and 2 pi. If you're in, especially if you're in Hawks. If you're in Hawks and you try to type this in as an answer for something that's supposed to be between 0 and 2 pi, it's going to tell you it's wrong because it's not, that's negative. It's not between 0 and 2 pi. So to get this angle that's down this way, instead of going this way, we're going to go this way to express it and use 2 pi minus the 0.4636. So this one we're going to get 4 solutions from 0 to 2 pi. We just have to be a little bit careful of how we get these other ones. So again, we added pi here to go from quadrant 1 to quadrant 3. And that's exactly what we did here, was we added pi to this answer to go from quadrant 4 to quadrant 2. And this just basically adds another pi to wrap it around in the positive direction instead of going in the negative direction. I'm going to do a couple of more with the calculator ones. I'll do one with sine and one with cosine as well. Any questions so far on that, though? All right, let's do another one with an identity here. Let's look right next door here at number 24. So number 24 here, we have cosine of 2 theta, and 5 cosine squared theta is equal to 2. Now, the problem with this one to start with is that we have mismatched arguments. These are not the same argument. Okay, so unlike the previous problem where we used an identity because we had different trig functions, in this one we have arguments that are different. When we still want to try to factor this, we need the same, not only do we need the same trig function, we need the same argument. We need to have this, the inside of the function to be the same. Luckily, we know an identity to replace this cosine of 2 theta with. We actually have 3 of them. But remember, if we're going to factor, we want to make sure that we have the same trig function all the way through. So for this one in particular, I want to replace it with 2 cosine squared theta minus 1. So that I end up with the same trig function with the same argument. So now let's see if we can simplify this a little bit. We get 7 cosine squared theta. When I add those two together, I'm going to try to isolate the cosine again. So I'm going to move the 1 to the other side to get 3. So we get cosine squared of theta is 3/7. So if we take the square root of both sides, we get either the positive square root of 3/7 or the negative square root of 3/7. Now, just like before, this is certainly not a value that we know the cosine of easily, right? We didn't learn any exact values that was square root of 3/7. So we're going to need to go over and grab our calculator again. So to get cosine by itself, I'll need to do to get theta by itself, I'll need to do the inverse cosine. The number on the inside was square root of 3 divided by 7. So we get 0.8571 about. I believe Hawks usually asks you for 4 decimal places, so I'm going to round it to the 4th decimal place there. So 0.8571. So go back over to where I was writing things down. So this one, when we do the inverse cosine of square root of 3/7, we get about 0.8571 for that one. Now, again, these problems are going to ask you either for the general solution, or they're going to ask you for all solutions from 0 to 2 pi, one or the other. This is, since we're doing the inverse cosine, this is an angle that's in quadrant 1. I know it's in quadrant 1 because it's positive. And inverse cosine only gives me an angle in quadrant 1 or quadrant 2. So again, if I think about the picture, let me erase, let's see if I can get rid of some things here so that I have some more room to work. Oops, that was not what I wanted to do. Let's undo that. Let's see if I can just erase this. Oops. No, maybe not. I'll just leave it. All right. Remember that inverse cosine gives you an angle in quadrant 1 or quadrant 4. So if I go up to an inverse cosine is quadrant 1 or quadrant 2, not quadrant 1 or quadrant 4. So if I go here, I would have an angle in quadrant 1 that gives me the 0.8571, like we talked about before. But there's another angle between 0 and 2 pi that gives me the same cosine, and that's the one that's down here, right? It's the one that's down in quadrant 4. So I need to go find this angle. Well, I know that this angle is the mirror image. It would be negative 0.8571. The issue with that, of course, is, like I mentioned before, when you're putting things into Hawks, it's going to ask you between 0 and 2 pi, and negatives aren't between 0 and 2 pi. So to get the angle that I need, I'm going to go around this way instead and write it as 2 pi minus that angle. Oops. Okay.
Can we type that exact thing in, or are we gonna have to like do 2 pi minus that in our calculator?
You probably, it's gonna ask you to round it to 4 decimal places. So my guess is you're gonna want to type it in your calculator. So I would just go back up to your calculator here and just do 2 pi minus the previous answer. And then that would be, so you would use the 5.4261 for that. My guess is it's going to make you do the decimal. But however, if you just typed in 2 pi minus the other decimal, it would probably just ask you that your answer is not simplified or something, because it should recognize that it's the right number. It just wants you to round it instead. But to be safe, it's just easier just to put the 2 pi minus that in your calculator quickly. Go back. All right. Actually, I'll just stay here. The other one was inverse cosine of the negative of the square root of 3 over 7. So remember when we do inverse cosine, we get an angle of either in quadrant 1, which is where we found the first one here, or we get an angle in quadrant 2. Since it's negative, this angle is going to be in quadrant 2. So this 2.2845 is over in quadrant 2. So if I go over here, this will give me theta is inverse cosine of the negative of root 3 over 7. And now I've already forgot what that number was, 2.28 something, 2845. So again, if I think about the picture, the angle that we just found is this one. But there's also one over in quadrant 3 here, right? Because we know that the cosine is also negative in quadrant 3. The inverse cosine only gave us the one that was in quadrant 2. We need to go find the one that's in quadrant 3. Good news is that we can do it the same way we did the other one. We can still just do 2 pi minus the 2.2845. The reason I know that is because, just like what I did over here, if I went this angle and measured this way, that would be the negative. So if I go around the positive way, it has to be 2 pi minus that. That's how I knew I just need to do 2 pi. So the good news is when you're doing the inverse cosine ones here, once you find one of the angles, the other one is you subtract it from 2 pi to find the other one. All right, questions on that one at all? So that one had a couple of different things that we wanted to illustrate. We had the replacing the cosine of 2 theta with the 2 cosine squared theta minus 1 to start with, and then also using our calculator to find the solutions from 0 to 2 pi. Let's see if I can find another one here with an identity. Let's look at 31 here. So this one has 4 times sine of 2x is equal to 3 cosine x. Notice again that we don't have the same trig function on both sides, right? I got a sine and I got a cosine. I also don't have the same argument. So this is telling me right here that I need to use an identity to rewrite the equation in a form that allows me to solve it. So I have an identity for sine of 2x. I can replace that with 2 sine x cosine x. And now again, don't be tempted to divide both sides by cosine. I see cosine on both sides, but if you divide both sides by cosine, you're going to lose some solutions. In particular, you're going to lose the solutions when cosine is equal to 0. The reason we don't want to do that is because we don't want to divide by 0, right? Dividing by 0 is a bad thing. So I don't want to divide by that variable piece. So instead, I want to collect everything on one side, because I want to try to solve this by factoring if I can. So we get 8 sine x cosine x minus 3 cosine x is equal to 0. We can factor a cosine x out of both pieces. We can set each piece equal to 0 now. So the second one, if we isolate the sine, we get sine of x is equal to 3 over 8. Now the first one we can solve like we've been doing because we know when cosine is equal to 0. We talked about that earlier, 20 minutes or so ago. X could be pi over 2. X could be 3 pi over 2. Those are the two places between 0 and 2 pi where the cosine is 0. And then again, if we want all solutions, we could add the 2n pi in here. That just depends on the directions for the problem. If the problem says find the general solution or find all solutions, you'll put in the plus 2n pi on there. If the problem just asks for the solutions from 0 to 2 pi, you'll just use the pi over 2 and the 3 pi over 2. Over here, for the second equation, I do not know where sine is equal to 3/8. So I'll need to take the inverse sine of 3/8. That's a job for the calculator. So go over to the calculator here. We'll do inverse sine of 3 divided by 8. That gives me 0.3844. So let me go back over to my sheet here. This was 0.3844. Now, remember again, we have to understand that the inverse sine function only gives me an angle in quadrant 1 or in quadrant 4. Since the number that we took the inverse sine of is positive, we found a quadrant 1 angle. That would be the 0.3844 here. But again, there's another spot from 0 to 2 pi where the sine is positive, and that's over here, right? That would be the quadrant 2 angle that has the same sign. This would have the same reference angle. This would be 0.3844 here. So to find the angle that we want from here to here, I need to do pi minus the 3.3844. And again, the reason why I know it's pi minus that is because I know that this angle over in the quadrant 2, that reference angle is the same as the angle we just found in quadrant 1. If I go all the way around, halfway around, that's pi. So I need to subtract off the 0.3844 to find the other one. So again, if we were looking for just the solutions from 0 to 2 pi for this equation, we would get these 4. Those would be your 4 solutions between 0 and 2 pi. If you wanted the general solution for this, you would just, again, stick on the plus 2n pi on the end of each of those, and that would give you a general solution. Questions on that at all?
Could you tell us again why you know it's pi minus that?
Sure. So the inverse sine function gave us this, the 0.3844 here. That was in quadrant 1, because remember again, the inverse sine only gives me an angle in quadrant 1 or quadrant 4, and since it's positive, it's going to give me the quadrant 1 angle. But I need to go hunting for the other one. I know that typically there are 2 angles that give me the same sine value between 0 and 2 pi. I know that sine is also positive over here in quadrant 2. And I know it's going to have the same reference angle. This is going to be the 0.3844 here. Okay. But remember, when we measure our angles, we always measure from positive x-axis around this way. So if I want to know what this angle is, that quadrant 2 angle. All the way, if I went all the way halfway around, that would be pi. But I don't want to go all the way to pi. I want to stop short. And this is how much short I want to stop. So I take that pi and subtract off the 0.3844. Does that make sense?
Yeah.
Okay. Other questions at all? All right, so your take-home quiz should open up at 11 on Moodle. So that'll be due on Friday at 5. So I'll do the same thing this Friday that I did last Friday. I will be on Zoom during our normal class time. If you want to stop by and ask questions, feel free to. When you're done with your take-home quiz, just snap pictures of it and upload it to Moodle for me, please. I will post another video later this afternoon with more examples of these trig equations so that you can see more of them. The solutions to this worksheet, so the solutions to all 34 of these problems should already be up on Moodle. I will double check and make sure that's right, but they already should be up there. So you should have solutions to all of these. Plus, I will have another video up there. There's already one extra video on YouTube as well. So you'll have an extra video, but you can, and then you can always reach out if you've got questions. So anything else before we stop? Say that again. I thought somebody said something. All right. Anyway, all right. Well, I will talk to you all later. Oh, Colin. Yeah. Yeah, Colin.
Can you send us your YouTube channel handle again? Because I didn't really use it much when we were meeting in class.
Yeah.
I haven't accessed it now. I'm going to watch some of those videos.
Yep, I can absolutely do that. Yep, I will do that.
Awesome. Thank you.
Yep, you're welcome. Anything else? All right, everybody. Have a good day. I'll talk to you later.
Thank you, Mrs. Davis.
Bye.